Okay, so this is group 7, the periodic table. Okay, this is the first part of group 7, the periodic table. Right, so what we've got on the periodic table, we've got fluorine. Be careful with your spelling of fluorine. Fluorine is F-L-U-O-R. Fluorine. Then you've got chlorine. And then we've got bromine. And then we've got iodine. And then the last one in group 7 is astatine. Okay, so first in group 7 you need to know the formula of these elements, and they are all diatomic molecules. All of group 7 are diatomic molecules. So when you write the element goes around in twos. There's 2 atoms, F2, Cl2, Br2, I2, and astatine 2 as well. Okay, so they're all diatomic molecules. So the element is written like that in a standard state. Okay, you need to know the physical state of these this group 7. Group 7 has got the name. Group 7 elements are called halogens. Group 7 are called halogens. Okay, and the physical state of their of the elements is fluorine is a gas, and chlorine is a gas, and bromine is a liquid, and iodine and astatine are solids. Okay, so what can you say? If those are the physical states, what can you say about the boiling point? What can you say about the boiling point of the group 7? What's the trend in boiling point of group 7 elements as you go down the group? Trend in boiling point of the group 7 elements. Okay, well, when you need to consider boiling point, you have to think about the structure of the elements. Okay, so if we take, just for example, we take chlorine. A chlorine molecule has got a Cl2, it's got a covalent bond between the 2 chlorine atoms, a covalent bond, and that's a chlorine molecule. Okay, but what's the structure of chlorine? And the same structure for all of the group 7 elements. Well, if you take that chlorine molecule and another chlorine molecule, okay, and what's between the chlorine molecules? Between the chlorine molecules is are weak van der Waals forces. Weak van der Waals forces. The weakest intermolecular force. And when you boil, when you reach the boiling point, you are breaking the weak intermolecular forces. You are not breaking the covalent bond, you're breaking the weak intermolecular forces. So this structure is called simple molecular. So it's covalent bond inside the molecule and weak van der Waals forces between the molecules. So when we boil it, we just separate the molecules and break the weak van der Waals forces. Now, you can probably see, because I've already given the physical states, that this one has the lowest boiling point because it's a gas, and it goes down to the highest boiling point. Okay, so the boiling point increases as you go down the group. The boiling point increases as you go down group 7. As you go down group 7. And that in an exam would just get you 1 mark. Okay, talking about the trend down group 7, it would just get you 1 mark. So you have to be able to explain why. Why does the boiling point increase as you go down? And it's something to do with the structure, the simple molecular structure. Okay, so we've said that when we want to boil, we have to break the weak van der Waals forces. But let's do a bit of revision. What causes the van der Waals forces? Why do van der Waals forces arise? So let's do a little bit of revision on van der Waals forces. van der Waals forces. Okay, so if you have an atom or a molecule, and you've got lots of electrons, and electrons are moving around the whole time, they're moving around, and you may get an unsymmetrical distribution of electrons, So that means they're moving all around, but for 1 instant, for 1 second, you might get more electrons on one side of the molecule than the other. And if that happens, and you get this unsymmetrical distribution, then you'll get a temporary dipole. And we write delta delta minus. It's a very small temporary dipole. So this means there's more electrons on one side than the other. And then relatively, the other side will become slightly positive. Remember that this is a dipole, and it just means slightly, delta. It just means it's delta, and it just means slightly, okay? So if you imagine in your classroom, and if all the students in your classroom, if they all got up and moved around the classroom, for 1 instant, there may be more people on one side of the room than the other. And that's created a temporary dipole, but then it disappears because you're all moving around. So it's very instantaneous, it's very temporary, and it's due to an unsymmetrical distribution of electrons. But as soon as it has happened, then in the neighboring molecule, in the next molecule, all the electrons are going to be repelled to the other side of the molecule. So this is going to create a dipole in the neighboring molecule. And so the word we use is induce. This is going to induce a dipole in the neighboring molecule, in the next molecule, in the neighboring molecule. Induce means make, create a dipole. And then that's going to happen in the next molecule, and it's going to pass on. But it's a very temporary thing, because the electrons are moving, and the dipole will go. And that is what van der Waals force is. It's very weak, and it's temporary. But if you again imagine in your classroom, if your classroom normally has 15 people in there, and 15 people are walking around the room, 15 electrons are walking around the room, and then there's 10 electrons on one side, that's not that big an effect. But if you had 100 people in your classroom, 100 people walking around, electrons walking around, then the effect would be a lot greater. Okay, so with van der Waals forces, more electrons will mean that the van der Waals forces, I'm just going to put van der Waals, safe keep writing it, the van der Waals forces will be stronger. Now be careful using stronger, they are weak forces. So you can say that there will be more van der Waals forces. There'll be more van der Waals forces rather than using stronger. Okay, so the more electrons, the greater the effect, more van der Waals forces. So let's go back to this question then. So that's the trend in boiling points. But why does this have the lowest boiling point? Why does this have the highest as you go down the group? Okay, so that's because as you go down the group, the boiling point increases because there are more electrons. Astatine has got a lot more electrons than fluorine, for example. And if you have more electrons, you're going to have more van der Waals forces. More van der Waals forces between the molecules, and therefore more energy is needed to separate the molecules. More energy is needed to break the forces. So a higher boiling point. And that's why. Okay, so not only do you need to know the trend of the groups in the periodic table, you need to be able to explain why. Okay, so that's a trend in boiling point. What about the trend in volatility? Volatility. So volatility, so what does that mean? So volatile, the word volatile in chemistry, what does that mean? So volatile means how easily something vaporizes, how easily something turns into a gas, how easily a chemical vaporizes. Something turns into a gas, can't fit it in, turns into a gas, Okay, so how easily something turns into a gas. So something that has a low boiling point. So for example, fluorine has a low boiling point. It will have a high volatility, which means it turns into a gas really easily, evaporates, turns into a gas really easily. Something with a high boiling point will have a low volatility. So these are like opposites of each other. So low boiling point turns into a gas easily high. High boiling point doesn't turn into a gas easily. So the volatility decreases, but the explanation is all related to the same explanation. Because if if something turns into a gas easily, then that must mean it's got very weak intermolecular forces between the molecules. Okay? Right, what else do we need to just start us off with group 7? This is just a start into group 7. So if these are called halogens, and these are the elements in their standard states, the elements, and these are the standard states of these elements, okay, what if you form an ion? If you take fluorine, what's the ion of fluorine? I'm going to use another piece of paper because I've run out of room. Okay, if you take fluorine, the ion of fluorine is the fluoride. It's called fluoride. Okay, if you take the ion of chlorine, it's called chloride, the ion. So this is when the element reacts. And then bromine is called bromide. And then iodine is called iodide. And then astatine is called astatide. Okay, so the ions are called halides. The elements are called halogens. The ions are called halides. Okay, so also finally, before we move on from this, you also need to know the electronic structure of group 7, and they're in the P block. The electronic structure, they're all in the P block. Group 7 is in the P block, and they all of the halogens all end in P5. So 2p5, 3p5, 4p5, etc. So that's the electronic structure. They all end in P5, right? And then back to the halides again, okay? So another question you could be asked is, if you look at group 7, the elements, group 7, which element is the most reactive? Okay, so which element is the most reactive? So let's go back. What we're going to do is just draw the elements again, just really quickly. Which element is the most reactive? Fluorine, chlorine, bromine, iodine, or astatine? Okay, which one is the most reactive? And when you're asked this question, you have to think, when a group 7 element reacts, how does it react? What happens to a group 7 element? Now, a group 7 element has got 7 electrons in the outer shell because it's group 7. Okay, 7 electrons in the outer shell. So when a group 7 element reacts, it wants to gain an electron in order to have a full shell. So this is what you're thinking. When you're thinking about reactivity, you're thinking about it needs to gain an electron. So which one of these elements is going to gain an electron the easiest, the best? Which one is going to gain an electron the easiest? Okay, so you've got to think about the number of shells and the shielding, about which one is going to gain an electron the easiest. Okay, so if we've got, let's just take for example fluorine. Okay, fluorine, Okay, fluorine is smaller. This is fluorine, a fluorine atom, just F, a fluorine atom. A fluorine atom has less shells, less shielding, and here's an electron which it wants to gain. Okay, and if you take an iodine atom, for example, an iodine atom is much larger. An iodine atom has more shells, and an iodine atom has more shielding. And which one is going to gain the electron the easiest? Okay, so an electron to be gained. Okay, so you can see that to gain an electron, it's about the attraction between the nucleus and the electron to be gained. The attraction between the nucleus and the electron to be gained. And you can see, because iodine is much larger, it's going to be harder to gain an electron than fluorine. Okay, so fluorine is the most reactive, and then fluorine is the most reactive, and then iodine is the least reactive, or well, actually astatine if you're going down the group. Okay, and the reason why, so let's just write this on the table. Let's try to clear it on the table. So the most reactive group 7 element is fluorine, is the most reactive, and the least reactive is down the bottom, astatine. Okay, and it's all to do with gaining electron. So as you go down the group, the atomic radius, this is of the atom, the fluorine, F, Cl, Br, I, just the atom. The atomic radius increases. And the shielding, so that means the number of shells increases, yeah? The number of shells increases, you could say. The number of shells increases as you go down the group. And then the atomic radius increases, but the shielding, the electron shielding also increases. So the ability to gain an electron, because that's what you're trying to do, you're trying to form a fluoride or a chloride. Ability to gain an electron decreases. So it's harder for astatine to gain electrons than it is for fluorine. So it's about the ease with which you can gain an electron. Okay, so fluorine is the most reactive and astatine is the least reactive. Okay, so if you think about group 2 is the opposite, because group 2, they're trying to lose electrons to have a full outer shell. Group 2 have got 2 outer electrons, and group 2 are trying to lose electrons. So the most reactive element in group 2 is going to be down the bottom of group 2, because it's the largest atom, and it can lose electrons the most easiest. Okay, final thing we're going to do before finish for the first part of group 7 is, if you have an unknown solution, right, but you do know it either contains chloride ions, bromide ions, or iodide ions. Okay, so it might be sodium chloride in solution, it might be sodium bromide in solution, or it might be sodium iodide in solution. And it's an unknown solution. You don't know which one it is. An unknown solution. You don't know which one it is, and you have to test. It comes in a bottle. It's not labelled, and you have to find out which solution it is. It's either sodium chloride, sodium bromide, sodium iodide. So it contains chloride ions, bromide ions, iodide ions, right? Because remember, when you've got a salt like this, in water, the salt will split up into ions when it's in water. So it'll split up into ions, okay? So you've got to do some tests. So how do you test for halide ions? What's the test, okay? So the first thing you do is you add silver nitrate solution. Okay, you add silver nitrate solution. That's silver nitrate. So you just get your test tube, you get your unknown halide in there, and you just add silver nitrate solution. Just very simple, silver nitrate solution. Okay, so right, so if that is chloride in there, if there's sodium chloride in there, what will happen is you'll get a white precipitate. A white precipitate. Be careful with your spelling, I'm not written that very well. Precipitate. And you'll know that is sodium chloride. If there is sodium bromide in there, then you'll get a cream coloured, so it's like an off-white, a cream coloured precipitate. And if there is sodium iodide, for example, or potassium iodide, which is an iodide, you'll get a yellow precipitate. Precipitate. And these are called, this is called precipitation reactions. Precipitation reactions, okay? So this is when two solutions, a precipitation reaction is when two solutions, so colorless, not colorless, sorry, so two clear solutions, they react together and they form a precipitate. React together and form a solid. A precipitate. Okay, precipitation reactions, okay? So I've got an unknown solution, I add silver nitrate, and if I get white precipitate, I know it's chloride, green precipitate, I know it's bromide, yellow precipitate, I know it's iodide, okay? And the reaction that's actually happening, the ionic equation for the reaction that is happening is that you have got the silver ions in solution aqueous reacting with the chloride ions solution aqueous, and that is making a precipitate, state symbol solid, and that's making a white, I'm just going to write PPT, precipitate of silver chloride, okay, silver chloride it's called, and that is what is happening. So if it was bromide, it would be silver bromide. If it's iodide, it'd be silver iodide, okay? Now, with these colors, when you're actually doing this experiment, it can be quite confusing, right? The white is quite clear, but the cream and the yellow particularly can be quite confusing, because when is something cream and when is something yellow? So what we need to do is do a further test. So you add silver nitrate solution and you get your precipitate in there. And then you're thinking, right, is this cream? Is this yellow? Is this white? I can't really tell. So then what you do is you add dilute ammonia. You add dilute ammonia. And what happens with dilute, this is aqueous ammonia, with dilute ammonia, the white precipitate will dissolve. And if that happens, you add dilute ammonia to the test tube, if the white precipitate dissolves, then you know that you have got chloride in there. Okay, you add dilute ammonia and nothing happens to the other two. So you go, all right, so let's ramp this up a little bit. Let's add concentrated ammonia instead. Let's add concentrated ammonia. And when you add concentrated ammonia, the cream precipitate will dissolve with concentrated ammonia, okay? But still nothing happens to this. So the yellow precipitate of silver iodide, nothing will happen in concentrated or dilute ammonia. So it does not dissolve in concentrated or dilute ammonia. And that's how you know you've got the yellow precipitate. Remember, these are the ions. It's actually not sodium, it's the chloride ion, bromide ion, iodide ion, the halide ions.